Hello, brilliant minds. This is your physics buddy, and I welcome back you all to this beautiful channel, Your Physics Buddy. In the previous sessions, we started work energy and power. This is going to be the fifth session on this, where we will be describing rotational kinetic energy and solving some important numericals on it. This channel has already covered a lot of units from honors physics curriculum. Do check them out. Do devote some time to acquire knowledge. Make sure you subscribe to the channel and hit the notification bell to follow the entire series. Stay tuned and let's do this.
Let's start today's session and we'll start with rotational kinetic energy. We'll talk about what rotational kinetic energy is. In order to understand rotational kinetic energy, there are few terms that we need to recollect. First, there is one term which is called moment of inertia. So, as of now, we didn't really talk about it, but what you can learn about this particular physical quantity is just like inertia, which gives the measure of quantity of motion or the quality of motion possessed by a body, moment of inertia is a measure of quality of rotational motion possessed by a body. Like we're talking about when a body is rotating. Like for example, suppose there's a fixed point, there's a point through which a line is passing, and from this point, which is lying on this axis, which is rotating with some velocity, angular velocity omega. So from this axis, which is rotating about with some angular velocity omega, we assume that there is a distance r at which a mass is placed. So with what is the quantity of rotational motion possessed by this mass? This is something we call moment of inertia. Inertia is represented by I, and it is equals to product of mass times square of distance between the mass and the axis of rotation. This is what we use for writing moment of inertia. What we need to understand here is for n number of masses, like if the system has so many masses, in that case, moment of inertia can be written as m1 r1 square, m2 r2 square, and this thing will go on up to mn rn square. The moment of inertia as a whole we can write summation of mi ri square, where I lying from 1 to n. So this is what we write for moment of inertia for a body having multiple masses rotating about a fixed axis of rotation. What's important here is to understand what is axis of rotation. Axis of rotation is the fixed axis about which the whole system is supposed to be rotating. So this is what moment of inertia is. So we have to talk about rotational kinetic energy. And here we can say, if we remember, like let us try to look at the diagram once again for a single mass. So suppose this was my mass, and this mass was rotating about the axis of rotation in this given path, like that. So at any point, if I observe the velocity of this body, what can I say? It must be tangential.
Yeah,
It must look like that. Whereas this is the distance from the axis of rotation. So do you remember what is the relation between omega, or you can say the angular velocity, and the linear velocity v? What relation did we study? Tell me.
uh, God. Check my notebook.
This was the relation between angular velocity and linear velocity. See, whatever we have learned in the previous units, we have to make sure that we remember each and everything.
Okay.
So this is the relation between angular velocity and linear velocity. And I already gave you that idea that how to remember these relations. I just gave you that thing that linear quantity is always equals to r times angular quantity. This is how you can remember it. Now, if we talk about linear quantity, we have so many linear quantities. Let's start with displacement. So linear displacement, if we represent it using S, it is always equals to r times angular displacement, that is theta. If we talk about linear velocity, it is always equals to r times angular velocity omega. If we talk about linear acceleration, it is equals to r times angular acceleration. So these are the relations that you can remember using this one. So this is how you are supposed to remember it. That is what I told you.
Fine.
Now we have to find out the rotational kinetic energy of this rotating body having some mass m if we assume. So how can we calculate it? So basically I'm giving you the derivation of half I omega square, that how we got half I omega square. So what we can do here is you can simply say the kinetic energy is going to be half mv square. Just think about this body. This body is rotating with some velocity v and the angular velocity omega at some distance r. So what we're going to do here is we know that kinetic energy is nothing but half mv square. Now if I try to write the value of v, what you can write in place of v? In place of v I can write omega r. That is going to be omega r whole square. So I can write it as half m omega square r square. So I can write it as half m r square times omega square. So we know mr square is nothing but I. The kinetic energy of a rotating body or a rotational kinetic energy of a body can be written as half I omega square, where this I is moment of inertia and this omega is angular velocity. Now always remember, whenever we are talking about angular velocity is always calculated about a fixed point. So we are talking about the same energy about a fixed point only. Does this make sense?
Yeah.
So it's not about only one particle. We do have more than one particle rotating about a fixed point with fixed velocity, fixed angular velocity. All right, so let me just give you a question. Suppose this is an axis of rotation about which all the particles must be rotating with some constant angular velocity, which is 5 radians per second, let's say. In the question, there are 3 different particles. One is supposed to be at 20 centimeter distance of mass 100 grams. One is supposed to be at 10 centimeter distance of mass 500 grams. One is supposed to be at 35 centimeters distance of mass 50 grams. The question is you have to find out the rotational kinetic energy of the whole system. So you have to find out the rotational kinetic energy of the whole system, assuming that these masses must be revolving in a fixed circular orbit like that. So you have to find out the rotational kinetic energy here. How can we do so? Tell me. What should I use to find this out?
Good thing.
See, whenever you are solving such questions, either you have to find velocity and plug it into the relation half mv square. Either you can use half pi omega square as well. But here you have to find out omega as well as I
Okay.
for individual masses. So what you can do here is If I just try to find out the rotational kinetic energy of the system, it is equals to rotational kinetic energy for first particle plus rotational kinetic energy for second particle plus rotational kinetic energy for third particle. For the first particle, I can write half I1 omega square. For second, I2 omega square. For third, again half I3 omega square. You can take out half omega square common, I1 plus I2 plus I3 in the brackets. So this will give me the rotational kinetic energy of the system. So you can now find out the values of I1, I2, I3. You know what is the value of omega square. You can substitute it into the equation and you can have your answer.
Okay.
This is how you're supposed to solve this. Got it?
Yeah.
Solve it and tell me what is the answer. Always remember, everything we have to put in SI units. We can't choose another unit for given components.
Okay. We got 0.19 joules.
So first of all, tell me what you got for omega square.
I mean, like the total inertia.
Omega square is 25. 5 square is 25.
Yeah, 25, and then 0.015.
0.015.
Actually,
Then,
no, like that's the total.
okay.
Well, I guess the whole thing would be 0.015125.
So it is going to be 0.2 square times 0.1. This is for the first one. That is going to be 0.1 square times 0.5, which is going to be 0.005.
Yeah.
And it is going to be 35 square, 0.35 square times 0.05.
Yeah, and then
You can't have this, I guess, 0.015.
well, when you add all of them, it equals. No, the
All
last
right.
one is 0.006, 125.
0.6125. No, not possible, I guess.
No, 0.006, 125. So it's
Hmm.
0.004 plus 0.005 plus 0.006.
All right. So what you can do is you can simply substitute the values in the relation, and you can have the rotational kinetic energy of the given system. This is how you're supposed to do it.
Mhm.
So let me just give you another question. Think about it, and if you did this, this means you understood all of the mechanics we have learned so far. Question is pretty simple. So suppose that there was an object. That object is supposed to be a ring.
Mhm.
This is a ring
Mhm.
of mass 2 kgs and radius 50 centimeters, placed at an inclined plane of vertical height 20 meters. The inclination angle is 30 degrees. You have to find out what is the angular velocity once it reaches the bottom of the incline. Find angular velocity of ring at the bottom of that incline.
Mhm.
Give it a try. What you need to remember is you need to remember the conservation of energy. If there is no force dissipating energy, then the energy is going to be conserved. So what you can use here, conservation of mechanical energy, that the energy at the top of the incline must be equals to the energy at the bottom of the incline. Think
Mm.
about from this point of view.
No, I don't think I had to do this one. You showed it.
Yeah. So always remember, if system is not experiencing any external force, just like in this case, there is no external force happening on the system. What you can do here is, as the system is not experiencing
Mm.
any external force, this implies that energy of the system must be constant. It should not change. And if it should not change, so we can say that the total mechanical energy at this point, let me say, must be equals to total mechanical energy at point 2. Now just think about it and tell me, at point 1, which energy do this ring must possess?
Uh-huh.
Which kind of energy it has at point A?
Mm. Centripetal.
No.
Oh wait,
Which
energy,
energy,
kinetic.
which en which energy it has?
Yeah, kinetic energy.
No, not kinetic. Kinetic energy is the energy which is due to the motion. At initially, the ring is at rest. Now, it has only potential energy at that point.
Right, right,
So
right.
that potential energy must be converting throughout the motion of the ring into translational kinetic energy as well as rotational kinetic energy. Are you getting it?
Yeah.
So the potential energy it possesses at point 1, it must be converted into translational kinetic energy, that is half mv square, plus rotational kinetic energy, that is half I omega square. Potential energy is something which is mgh. So we know these relations. We already studied all of them. What we need to understand here is that how this energy is being converted from one form to another. That's it. If you understood this, it is good to go. So what we can do here is now, first of all, we need to find out the velocity. Otherwise, we won't be able to find out the omega. So how can we find out velocity? That is translational velocity by simply using equations of motion. So what we know here is that the translational kinetic energy is always, you can say, it can be calculated using v square minus u square is equals to 2gh. So v square is something we have to find. Initially, it was supposed to be at rest. We just dropped it, and it rolls under its own weight. So v is going to be root 2gh. That is going to be root 2 times, I'm taking gs 10, h is 20. That is going to be 400, that is 20 meters per second. So the velocity it will possess at the bottom, it is going to be 20 meters per second.
All right.
We can write half into 2 into 20 square plus. What about I? What can I write about I? So remember, the moment of inertia for ring is mr square. For other objects, it is different, but for ring, it is mr square. So I'm taking this example only. So what you can write here is the mass is given as 2. The radius is 50 centimeters. I can take it as 0.5 square omega square. This is what you have to find omega. What about mgh? Mgh is going to be 2 into 10 into 20. I'm taking again gs 10. Now, the important part here is velocity with which it will go here. It is not going to be 20 because this is a relation we use when we are dropping something from a certain height. We cannot substitute velocity 20 here. So this question can be solved only if the velocity at the bottom is given. If there is no velocity, we cannot solve it. So let me just make few changes to the question. And let us assume that the velocity at the bottom is already given in the question, which is 5 meters per second. Let's assume, just assuming. So you can substitute all the values and you can find out the value of omega from this relation. The most important part to remember is if there is no external force acting on the system, total energy of the system remains constant or conserved. There is no change in the energy. That is what you have to remember. Does it make sense?
Yeah.
So this is conservation of mechanical energy, and that conservation of mechanical energy is always written or done only when net force acting on the system is zero. There is no external force acting on the system. That is something you need to keep in your mind.
Mm-hmm.
Let's talk more about it. More about conservation of mechanical energy. So when we're talking about work energy theorem, we simply said that whatever work is done by an external force on a system is equals to the change in kinetic energy produced. But if we talk about conservation of mechanical energy, we'll simply say if net external force acting on the system is zero, if net external force acting on the system is zero,
Mm-hmm.
then total energy remains conserved. So total mechanical energy it possesses initially must be equals to total mechanical energy it possesses finally. So this thing can be learned from various examples. Example 1. If you dropped something from a certain height, something of mass from a certain height, energy throughout the motion remains conserved. And we do have a proper derivation part to prove this statement. Like for example, if there is an object which is above the ground at a certain height h and we dropped it. So throughout the motion, this mass m, the energy it is going to possess, it is going to be constant. So at point 1, it is constant, at point 2, it is constant, at point 3, it is constant. But if we talk about the energy conversion between 1 and 3rd, we will find out that at point 1, it must possess potential energy due to its height. This whole potential energy must be converted into kinetic energy at point 3. Because at point 3, it only has kinetic energy. Whereas if we talk about the second point, at second point, it too have some fraction of kinetic energy as well as some fraction of potential energy. So that is what you need to keep in mind. Apart from this, we can take another example, an example of simple pendulum. So for example, suppose there is a simple pendulum. This is a bob of mass m. Now what we did is we just push the bob by applying some external force and keep it till here. And once it reaches this point, it is known as the extreme position. We just dropped it from this position. Now what this bob is going to do? It is going to rotate this way forever if there is no external dissipation of energy in the system. It will rotate in such a way that the energy remains conserved. It means if we consider it as the ground level or the reference point, so whatever elevation we provided, in terms of height, it must gain some potential energy. And this potential energy is going to convert into kinetic energy at this point. And again, once it reaches here, this kinetic energy is going to convert into potential energy. So this conversion of energy takes place if there is no external force or agency to dissipate its energy. And that energy dissipation is generally observed in the form of heat. And sometimes this energy dissipation is due to the frictional force or friction losses. So we need to keep this thing in mind that whenever we are talking about a system in which there is no external force acting or there is no resistive forces present, so in that kind of system, energy remains constant. And we do observe conversion of energy between kinetic and potential in the system, within the system only for the same particle because of the position change. So these two examples are the best example to show how mechanical energy is conserved. And always remember, whenever we are calculating energy, we are calculating energy from the point of view of reference level. So reference level is very important. Without understanding reference level, we cannot identify which energy object possesses. Like for example, we were talking about gravitational potential energy earlier on. And according to gravitational potential energy, we always take one reference. And that reference is supposed to be surface of Earth. So we can call it reference line. And that reference line is generally surface of Earth. Like why I'm saying this, suppose this is Earth having some radius r, and this is my object placed at some height h. So if we're talking about the gravitational potential energy in this case, we can simply write it as mgh. But what this mgh is? This mgh is actually the change in potential energy between the 2 points. Which are the 2 points? The 2 points are the surface of Earth, and one is that of the height at which the object is. That is the change in potential energy, and that change in potential energy, that is delta U, can also be written as mgh. But how do we calculate it? With a reference line, with respect to the reference line. With respect to the reference line only, we gave it as mgh because from the reference line it is h height above. So when we are writing this formula mgh, so we have already considered that reference line for this particular case is going to be the surface of Earth. Without considering this, we cannot have this. Otherwise, gravitational potential energy in this case is going to be, I guess we already discussed it. Gravitational potential energy in this case is going to be G
G.
m m over r, that too of negative.
Yeah.
We discussed the same for the satellite as well. So the relation is going to be same. So this negative of G m over r is nothing but mgh. Apart from this, if we talk about a small g, like acceleration due to gravity, what is this small g going to be? Now, we know that Earth is going to pull the object towards itself with some gravitational force, that is Fg. This gravitational force can be written as G m m over r square. Apart from this, we also know gravitational force is nothing but mg. If you substitute both the relations, we get mg is equals to G m m over r square. From here, we can get the value of small g, which is going to be G m over r square. If we substitute this value of g in this relation somehow, just look at it. Let us just substitute the value of r here, or you can say gm here. Gm is going to be gr square. Let us substitute the value of gm in this relation. So we are going to have gm, in place of gm I am writing gr square m over r. Now this r is something we can write it as radius of Earth if the object is close to the surface of Earth, or if this h is like very small in comparison to radius of Earth. So we can write this as gr square m over r only. So it is going to be mgr. So this mgr or this mgh is the same thing. There we are talking about in terms of height. Here we are talking about for the surface of Earth. Here there is, or you can say, which is at the surface of Earth or at radius r. So this is what reference level is. Apart from this, we can also talk about this one thing which is called thermal energy. So always remember, if a system possesses any retarding force, So what they will do? They dissipates energy in the form of thermal energy. Most important force responsible for this thermal energy production is the friction. Friction is the cause of thermal energy in 95% of cases. If there is a friction, there will be some thermal energy. You can understand this. Are you getting it? Like, for example, if an object is sliding, friction is continuously acting in the backward direction. So what this friction is doing? Friction is opposing the motion. And as it opposes the motion, it actually causes the surface
Mm.
to produce heat or thermal energy. Or we can say, or we can define thermal energy in this way. If two surfaces are rubbing against each other, then we can say total energy must not be conserved, or some mechanical energy must get lost in the form of heat. In order to visualize it, you can also remember that whenever you're driving a car or vehicle, after a certain time, after a certain period of time, the car heats up. Why it heats up? Because there are so many resistive forces present in the system of car which actually converts some of its energy into thermal energy. And that thermal energy is something which we always want to minimize. And that minimization can only be done if resistive forces can be eliminated. If resistive forces are eliminated, this can be done.
Okay.
Or you can say thermal energy will not be observed. So quite simple things, but yeah, you have to understand each one of them.
All right.
So as you said, whatever topics we have studied so far, we talked about all the forms of energy, we talked about conservation of energy, we talked about mechanical energy. We didn't talk about elastic collision, inelastic collision, and machines, as they are not the part of this times exams. So we can skip it. Now, what I will suggest you to do is practice as many things, as many questions as you can. Like you have the book, use the Inspired Physics book, try to solve each and every question you have in the book.